All right, hi everyone, and welcome to today's seminar. Today we have two speakers, Shannon Killey and Jürgen Matzka. Our first speaker of the day will be Shannon. Shannon is a second-year PhD candidate at Northumbria University in Newcastle, United Kingdom. She is currently doing research on particle distributions in the Earth's radiation belt, focusing on applying modern techniques such as machine learning to space plasma data in order to investigate the dynamics of the Van Allen belt's relativistic electrons. So today I'm happy to have Shannon here to talk with us about her recent research diagnosing relativistic electron distributions in the Van Allen radiation belts using machine learning. Shannon, if you'd like to take it away.
Thank you very much for inviting me, Kyle. I'm really excited to talk to you all today. So as Kyle said, I'm a second-year PhD student at Northumbria University in the UK. And I'm going to talk to you about how we can diagnose the relativistic electrons in the Van Allen belts using machine learning. So to start with, the Van Allen belts are these toroidal plasma regions that surround the Earth. There are typically two belts, simply named the inner and the outer belt. The inner belt lies approximately 1 to 2 Earth radii and is predominantly populated by relativistic protons with energies in the ranges of tens of megaelectron volts to gigaelectron volts. Our outer belt lies at approximately 3 Earth radii and can extend all the way up until 7. It is predominantly populated by energetic electrons with energies in the range of hundreds of kiloelectron volts to tens
Hi, Shannon. You're cutting in and out.
Yeah, sorry, my Zoom just cut out. Let me just start sharing again.
Yep.
Okie dokie. Sorry about this.
No worries.
Okie dokie. Can you see my slide again?
Yeah, we're back into presentation mode.
Perfect. Okay, so then go back to the outer belt. These are populated predominantly by energetic electrons with energies in the range of hundreds of kiloelectron volts to tens of megaelectron volts. My slide stopped. Okay. So the radiation belts are highly dynamic, and this is because the relativistic particles that inhabit the belts are driven by physical magnetospheric processes, such as acceleration, transport, and losses at different energies and different pitch angles. This means that different processes result in differently shaped particle pitch angle distributions. And particle pitch angle distributions are really important to understand as they can help us understand the plasma conditions and therefore further understand the behavior of the energetic particles that populate the radiation belts, and in the case of this study in particular, the relativistic electrons. So as I said, there are different magnetospheric processes that result in differently shaped pitch angle distributions. One example of a physical driver is our wave-particle interactions. So if you look at this diagram on the left, as our electron drifts around the Earth every few minutes, it will encounter different waves. And these different waves result in differently shaped pitch angle distributions. And when I'm talking about a pitch angle distribution, I'm referring to the diagrams like I've shown here, where we have energy plotted along the x-axis, pitch angle plotted along the y-axis, and the colour represents the relativistic electron flux. Here I'm showing 3 different examples of the shapes that we expect to see. So first we have our butterfly distributions, which has a decrease in flux at 90 degrees. And these are thought to have been caused by things like night side wave particle interactions or something called magnetopole shadowing. Then we have our pancake distributions, which have a peak centered on 90 degrees. And these types of distributions are thought to be caused by day side wave particle interactions or radial diffusion. Our third example is our flat top distributions, which are thought to be an intermediate phase between a butterfly and a pancake, where there is a flux plateau centered across 90 degrees. And this type of distribution is caused by dawn and dusk sector wave particle interactions. Now, the aim of my study was to try and determine the shapes of the different pitch angle distributions without preemptively defining their shape or their number. And to do this, we applied a series of unsupervised machine learning to 7 years worth of RET data collected by the Van Allen probe mission. So the Van Allen probe mission consists of 2 spacecraft named A and B, which collected flux measurements between September of 2012 to July of 2019 every few minutes, meaning that there are almost 20 million observations in total per probe. Now, even though there are 2 spacecrafts, my research only focused on Van Allen probe B. An example of what the RET data looks like is shown here, where we have L star plotted on the y-axis and time plotted on the x-axis. The colour represents the relativistic electron flux measured at 1.8 megaelectron volts and 90 degrees. Now notice how I mentioned the flux taken at a specific energy and a specific pitch angle. And this is because REPT measured flux with respect to 17 different pitch angles and 12 different energies, meaning for each of the 20 million observations, we have a flux measurement with respect to 204 different pitch angle energy combinations. And we call these combinations dimensions. So for each of our 20 million observations, we have a diagram that looks a little bit like this, where we have our 12 energy bins along the x-axis, our 17 pitch angled bins along the y-axis, and here the colour represents the normalized electron flux. Now, manually going through 20 million observations, each with 204 dimensions, is a rather long and lengthy process, and so we employ a series of machine learning to help make this task a little bit easier. So we first needed to process our data in a format that our machine learning can use. We first normalized our data. So we took the maximum flux measurement of each observation so that all of our measurements fall between 0 and 1. As we have 204 dimensions with respect to 12 different pitch angles, 12 different energies and 17 different pitch angles, that meant our data array had a shape of 12 by 17 by 20 million. And so we flattened the array so it was a little easier for processing. So we now only have a shape of 204 by 20 million. And when using machine learning, it is good practice to split your data set into a training, validation, and testing set. And by doing so, we took a 20-20-60 split, meaning for our training and validation sets, we have approximately 4 million observations in each, leaving approximately 12 million observations for our testing set. Now, 204 dimensions per observation is rather difficult to interpret, so we wanted to reduce the number of dimensions, and to do this we first applied an autoencoder. So an autoencoder is a form of a neural network, and in the case of our study is formed of an input, a hidden encoded layer, and an output reconstruction layer. Each one of these circles represents a neuron, and in our specific case, each neuron represents one of the 204 dimensions. You'll notice our input and output layers have the same number of dimensions, and this is because the reconstruction is a direct replica of the original input data, solely formed on the information from the encoded layer. And our encoded layer is what has our lower number of dimensions and how we compress our data. And autoencoders are really good because they are really efficient at identifying both the linear and non-linear relationship within the data, while also minimizing the amount of information that is lost during the compression. So we used the autoencoder to compress our 204 dimensions into only 102. However, 102 dimensions is still quite difficult to visualize, so we want to further compress this number down, and to do so, we applied principal component analysis. And principal component analysis works by first calculating the covariance matrix of the data itself. It then computes the eigenvectors of the covariance matrix, and these are known as principal components. And due to the hierarchical nature of the eigenvectors being returned, the top n components are considered to be the most important, as they contain the most information. Now, the number of principal components directly correlates to the number of dimensions. So to further compress the number of dimensions of the data, we took the top 3 dimensions and therefore the top 3 principal components. And we applied PCA after an autoencoder, as we wanted to ensure that we're retaining the most important information. It's also pretty handy in identifying any further linear relationships in our data. And the resulting 3-dimensional representation of our rep data is shown here, where each one of these axes corresponds to a principal component and therefore one of our dimensions. Each one of these individual dots represents one of the 12 million observations in our testing set. But from this, we can see that because they are so densely packed, we cannot determine which observations are similar from this diagram alone. So therefore, we need to find a way to somehow group the data into similar groups. And as this is an unsupervised learning problem, we don't know how many groups there are or what similarities we should be looking for. Therefore, we need to employ a method that can both predict the number of clusters or classifications we have, and then to organize our data into these groups. And to do so, we use 2 types of unsupervised clustering techniques. The first we used was a mean shift algorithm, which predicted the number of clusters in our data, before we then applied this number to our data using a k-means algorithm. Now, mean shift is really great as it only relies on the density function of the data, so it does not rely on any external parameters. It works by iterating between calculating and translating the mean shift vector of each data point until they converge on a density function mode. So if you look at my very terribly drawn density function at the bottom, where we have 2 peaks, we can see that for our 4 data points, x, there is a tiny arrow underneath each one, which represents the direction of the nearest density function maximum. As we iterate through, we can see that these start to converge onto our density function maxima. Once this has been completed, the number of nodes corresponds to the predicted number of clusters in our data set. We then apply this number using a k-means algorithm. A k-means algorithm works by first randomly assigning k centroid positions within our data. It then iterates between calculating the Euclidean distance between each data point and each centroid position. Then it assigns each data point to its nearest centroid, before it then recalculates the centroid position of each cluster. The cycle will keep continuing until there's no variance in the centroid position, and therefore we have classified our data. So when we applied this to our 3-dimensional rept data, we found that there were 8 different clusters. And we can see these clusters in our 3-dimensional representation shown here, where once again, the axes reflect the 3 principal components, and this time the observations have been colored corresponding to their cluster number. As the data is really dense, these clusters are not significantly spatially separated, meaning that at the boundaries, the observations may have been misclassified. Therefore, to limit the chance of misclassification, we have applied a 95% confidence interval to our clusters in Euclidean space. This now means that our clusters are a lot more spherically shaped and they're slightly more spatially separated. If you are interested in how we use the method in more detail, we have recently submitted our paper to RASTI, and you can read our preprint from the QR code here. I will also put the QR code on it again at the end, so you can grab it then. So then, now that we have our 8 different clusters, we then wanted to determine what the significance of each cluster was. And to do that, we plotted the mean pitch angle distribution across all energies. And that looked a little bit like this. So from these 8 different distributions, we can see that they all have a slightly different shape. We have 2 types of pancake distributions, where one has a slightly more cigar-shaped. We have 2 different types of flat tops, where one extends into the mid-energy ranges. We have 2 types of butterfly distributions, where one has a very significant high-energy flat top. And finally, we have 2 remaining clusters that showed a faint flat top and a faint pancake. And when we looked at the observations within these clusters, we determined that they only contained noise or significantly low counts, which were close to the noise floor of the instrument. And therefore, we have inadvertently denoised our data and can neglect these observations from further study. So just to kind of show you the shapes that I am seeing in the full energy range, here is the pitch angle distributions at 1.8 mega electron volts only. We have pitch angle plotted along the x-axis and the mean normalized flux plotted on the y-axis. I have noted their shape underneath so that you can see the shapes I am looking at. So now that we know that we have 6 scientific pitch angle distributions to consider, we then wanted to see where these clusters were in space. And to do so, we plotted MLT versus L, with the colour representing the occurrence of the observations. What we can see from these fixed figures is that our pancake type distributions are very dominant on the day side of the Earth, which is noted by this white semicircle. Our butterfly distributions are along the night side of the Earth, which is noted by the black semicircle. And one of our flat top distributions kind of shows an intermediate phase between a pancake and a butterfly by having dominant occurrences in the dawn and dusk sectors. Our mid-energy flat tops, however, lie at all MLT, but very dominantly along an L shell of approximately 3. And our butterfly and flat top seems to have 2 distinct features. And for this reason, even though all of these clusters are very exciting, we are just going to talk about this one cluster. As I said, it's because we have 2 distinct features. We have one feature that happens at high L on the night side, and another feature that happens at low L in all MLT. And when we look at the L shells that we're looking at, these correspond to observations in the inner belt. As we said earlier, the inner belt predominantly consists of relativistic protons, meaning that our relativistic electron observations have likely encountered some proton contamination here. So therefore, we wanted to separate these 2 instances and replot their mean pitch angle distributions. And when we did so, we could see that at low L for all MLT, we can see that there is still a very faint, weak butterfly at low energies, but a very predominant flat top at high energies. And this feature is not present in our high L night side distribution. This to me suggests that this is our signature of proton contamination. Our high L night side distribution has a very distinct butterfly. This now leads to the question of why weren't these observations classified with our other butterfly cluster? When we look at these 2, we can see that they have slightly different pitch angle peaks. So our butterfly cluster that we just looked at has a peak of approximately 35 degrees compared to our butterfly cluster from before, which has a peak at approximately 65 degrees. Now, the differences in these 2 different pitch angles suggests that they have been caused by 2 different magnetospheric phenomena. And this is supported by the work of Ozeki et al. Of 2022, who associated butterflies at 35 degrees with magnetopole shadowing, and butterflies at 65 degrees with wave-particle interactions with chorus or magnetosonic waves. So now that we know the different types of clusters and where they are, we then wanted to see how they change in time and space. And to do so, we plotted L star again on the y-axis and time on the x-axis with respect to the relativistic electron flux taken at 1.8 megaelectronvolts and 90 degrees on the top, and our cluster number on the bottom. Now, ignoring our observations of the inner belt, because these have likely been experienced proton contamination, and solely looking at the outer belt, we can see that due to the high number of observations, there's approximately 12 million in this figure, it's really difficult to know any dependence on cluster. The exception being this teal cluster 3, which corresponds to our mid-energy flat tops, which seem to line the inner edge of the outer belt. Now, to determine if there's any other sort of dependence from our clusters, we thought to separate the observations. So here we have our 6 clusters with respect to L star and time. And what we can see in our pancake and our flat top observations is that these occur very predominantly throughout all 7 years of the Van Allen probe mission, and typically at all L star in the outer belt. Our cigar shape distributions, however, are very dominant along the outer edge of the outer belt, except for instances of intense flux enhancement. Our 65-degree butterflies, which we associated with wave-particle interactions, are very consistent throughout the 7 years. However, they kind of lie in the very heart of the outer belt, which is completely different to our 35-degree butterflies, which was due to magnetopole shadowing, which have more localized observations in the outer edge of the outer radiation belt. Now, looking at these 6 diagrams, we can kind of infer an evolution of pitch angle distributions between pancake, cigar, flat top, and butterflies. However, to further investigate the potential evolution, we will have to look at a more isolated time. So further work from this study will be to isolate storm times to try and evidence any pitch angle distribution evolution. So therefore, just to summarize everything we've talked about, we have applied a series of unsupervised clustering techniques to Van Allen probe rect data in order to classify 6 different pitch angle distributions. In these 6 different clusters, we have identified 2 different types of butterflies, which correspond to 2 different types of magnetospheric drivers. Future work will be to try and determine any other mechanisms that drive each cluster, and to try and evidence this potential evolution of pitch angle distributions, particularly during storm times. And again, if you are interested in reading the paper, the QR code is here. Thank you very much.
Hi, Shannon. Thanks for a great talk. That was really cool. It's quite neat to see how well the methodology was able to pull out very well-known pitch angle distributions. So we have a couple questions. The first comes from Eric. He's wondering, for the principal component analysis, the number of dimensions you chose, was that a priori, or was that something that just came out of the principal component analysis, that those were significantly larger than the other eigenvectors?
The goal of using the principal component analysis was that we wanted to try and visualize all the data together. So we originally chose 3 dimensions, as you can plot a 3-dimensional graph. However, we wanted to check whether this was a good number to use. So we also tried it with 4 dimensions and with 2 dimensions. And the difference between 4 and 3 dimensions was only like 4%. So we said that using 3 dimensions was enough to kind of capture the most important information.
Mm-hmm. Yeah, cool. Jason has a follow-up to kind of your conclusion side here. Have you separated your observations into different drivers yet, such as storm times, substorms, steady magnetospheric convection, etc.?
Yes, that is literally the next step. So I was going to actually speak to you about your storm lists, for example, to see if we can start subdividing our times into different storms and things, see if anything specific comes out. But yeah, cool. Great suggestion.
So Lynn has a question regarding the signal to noise. The signal to noise ratio, do you see it as being an issue and that the code is chasing the noise, or rather was the code really easily able to separate out the noise from the rest of the signal?
So the whole idea was that we didn't want to manually do anything with our data beforehand other than normalizing and flattening. So even the noisy observations are included, but we found that when we did our clustering algorithm is that it clustered all the noise as one cluster. And then anything that had low counts, so like less than 1,000, was all clustered as another cluster. So by doing so, we've actually managed to denoise our data that way. I hope that makes sense.
Yeah, so it doesn't so much as chase it as it does identify it while still being robust to the other pitch angle distributions. I have one more question. I thought it was kind of answered, but then you had you attributed the difference to proton contamination. But in the pitch angle distributions as a function of energy, do you ever see two different pitch angle distributions at different energies, or is the pitch angle distribution quite constant across as a function of energy?
Do you mean in, sorry, let me scroll all the way back, in these ones?
Yeah, so this is just more of a general pitch angle distribution question. Like, is it possible to get a pancake at low energies and a butterfly at higher energies? Or is the pitch angle distribution generally just constant across energy?
The pitch angles are done in bins, so they're measured across all energies. But as you can see in these types of diagrams at very high relativist, like super relativistic energies, you're not really identifying much flux, and therefore you can't really see any sort of shape in the pitch angle. Does that make sense?
Yeah. Okay, so we're almost at time, but Dave Stuybeck has one more question. There have been reports of butterfly distributions on the inner edge of the radiation belt when the magnetopause is greatly compressed. Did your magnetopause shadowing butterfly distribution show anything that close in?
So let's have a look. So these are the ones that are attributed to magnetopause shadowing. So there may be some observations within this. It could just be the way the color bar is. But when we look at the L star, we can see in the bottom right here that there are a few instances along the inner edge, and as well as possibly a couple along the outer edge of the inner belt. However, we're not sure how accurate they are due to proton contamination. We're hoping to look into that cluster a little bit further as well. So,
yeah. So David is curious about the day side. I think this is the plot where we would have it, but unfortunately we don't have any. There's no MLT information in this one. But that might be something worth investigating in the future.
Yeah, definitely. Thank you for the suggestion.
All right, excellent. So just in interest of time, sorry, Shannon, to cut you off there, but we'll move on to Jürgen's talk now. So our next speaker is Jrgen Matzka. Jürgen studied geophysics and completed his PhD at the University of Munich, and then moved to the Danish Meteorological Institute, and then later the Technical University of Denmark, where he worked with the Greenland magnetometer chain and various magnetic observatories. In 2014, he headed to the GSC Potsdam and was responsible for one of the global magnetometer networks, as well as the derivation of the International KP Index. In 2022, Jürgen started a consulting company, Leo Magnetics, specializing in magnetometer data, ionospheric and upper atmosphere satellite and ground station data, as well as space weather. Today, I'm happy to have Jürgen here to talk to us about the new KP-like geomagnetic indices that he has been working on and developing over the last few years. Jürgen, if you'd like to take it away.
Thank you very much, Kyle. Hello, everybody. My name is Jürgen Matzka. I'm working for GFC, German Research Center for Geosciences. That's my main job. And I would like to talk to you about the KP index and our new KP-like geomagnetic indices with some new features which we think are very useful. There have been quite a few contributors to this publication. They are all the co-authors of the two publications shown here. So I would like especially to mention Claudia Stolle, Yosuke Yamazaki, here who have been working on the science side, and other colleagues here, they are more on the operational side and have developed the new indices. The two papers, one is in space weather, describe the KP index, and the other one is in geophysical research letters, describes new HPO index, with Yosuke Yamazaki being the main author for that one. Well, just a short introduction to our geomagnetic observatory. NIMEC is 60 kilometers south of Berlin. The observatory was established in 1930, and its geomagnetic latitude is 48 degrees north. And it is actually the standard observatory for the so-called K indices. So all the other K indices of other observatories relate to the NIMEC K scale. It only became a proper KP station, so contributing to the planetary K index in 1988. Since 1997, we are producing the officially recognized KP index, and since 2020, we also distribute the HPO index, which was developed in the EU Horizon 2020 project. And besides of our work with the indices, we take care of more than 15 geomagnetic observatories worldwide. I also want to share this slide with you. The red dots are observatories that we operate. Many of them are in cooperation with local institutes. We are especially interested in the Atlantic hemisphere, down here to the South Atlantic anomaly. We are very interested in the geomagnetic equator also. We have stations here in South America, and low latitude stations in the Indian sector. Right, and we also have a station in Antarctica, Normalize station, and one of my new favorite projects is actually to put more geospace instrumentation there in the near future. But let's talk about KP. So KP as an index was established by Bartels, and he published that in 1949. It's a planetary index. That means it's a combination from observatories worldwide, and it's valid for the whole world. It's a 3-hourly index. Here on the plot, you see one UT day, and for each UT 3-hour interval, one index value is defined. The values go from 0 to 9 in steps of 1/3. You can get KP values back to 1932 from our archives, but we also distribute a very fast near real-time version of KP. And this is something similar also done by NOAA. They produce the so-called estimated KP index, which is also used by many people. As I said, KP is based on K indices. They are standardized. I will talk about this later again. And they come from 13 subaurora geomagnetic observatories. So these K indices, they are station-specific indices. They are also 3-hourly. And KP is used a lot in the community. It is the basis for one of the NOAA space weather scales, for example. It is used for many space weather services. Many studies and publications are using it. And it's also a very important input parameter for many geospace models. Now, talking about the KP stations, these are 13 geomagnetic observatories, which have to be very reliable and come with a long-term commitment. But as you see on the red dots here on the global map, it's actually a pretty uneven longitudinal and hemispheric distribution. And the reason in this is also in politics. This is from the time of the Cold War. So it was heavily emphasized on stations in the West and in Australia and New Zealand. And in order to mitigate this effect, there is a certain standardization procedure, which is important to reduce or taking into account the local time and the season and the hemisphere of the observation. So any K value is kind of recalculated to a standardized value. And then 13 observatories together, they produce the mean value, and that's the KP. Having said that, these observatories should be very reliable. Nevertheless, 8 of the 13 stations have been relocated since 1932, and they are shown as the old observatory locations in blue and the new ones in red in the bottom plots here. So the majority of stations actually has changed during KP, has changed slightly in position. Now, how is the K value, the underlying parameter for KP, determined? In the top panel, you can see in blue the geomagnetic field recordings of the north component X at the observatory NIMEC. And the black curve shown here is the so-called quiet curve. That is determined by an algorithm. It's a kind of a smoothing. And after subtracting the quiet curve from the blue magnetic field measurements, we get the blue curve in the middle panel, shown here, which is called the K variation or magnetic disturbance. And here I have plotted for each 3-hour interval a box, a red colored box, which starts and ends at the start and end of the 3-hour interval, and which goes from the maximum value of the K variation to the minimum value. And the number on top, for example, here 49, that is the difference in nanotesla between those 2 points. So that's a range of 49 nanotesla in this time interval. And the same is also done with the Y component, shown here in the bottom plot. And then for each time interval, the larger number of ranges chosen, in this case, the interval here, it would be 49 nanotesla. And that is mapped in a quasi-logarithmic way onto a K value, onto this index value. So if the range is in between a certain boundary, then it will get a K value of 4. This range mapping is latitude dependent. So stations that are at higher latitudes have similar K values as stations at lower latitudes. And what you can also observe here, that's important for later, if you shorten the time interval for which the K values are produced, of course, the range usually gets smaller. And the new indices, they have shorter time ranges, so this is something we have to take into account. Now, this is a huge table, but we will make it very fast. This table only shows KP values starting from 0 on the top left and going to 9 on the bottom right side. Often people, because KP comes in units of thirds, often people like to calculate with 3 times KP, so you have a convenient integer number going from 0 to 27. And I want also to mention here that KP is a logarithmic or almost logarithmic number. That's not very convenient when you want to produce things like mean values. So there is also a linear version of this AP, of the KP, which is called AP. And for example, here for a KP value of 0, the AP is 0. For a KP value of 9, the AP value is 400. And there is also one line here with the frequency distribution of the KP values. And I just show this here because it was very important for Bartels when he designed the index to have a useful frequency distribution. So for example, about 3 to 4% of all index values, they show true geomagnetic quietness. and so on. The most frequent KP value is 1, with almost 9% of the index values here. And there is also a debate about the units of the AP index. So according to Bartels, it has units of 2 nanotesla, but others like Siebert and including myself, we recommend to regard it as a dimensionless number without any problem. Right, KP properties. So on the top left plot, you can see since 1932, you can see the sunspot numbers. In gray, you see the individual solar cycles here, and you can see mean KP values, which of course have been calculated not directly from KP values, but have been changed to AP values. Mean AP was calculated, and then the corresponding KP value is given. And you can see as the well-known feature that during the declining phase of the solar cycle, you have maximum KP values, and you can actually also very nicely see how low the mean KP value has been during 2008, where we had very few sunspots. Here, another important property of KP is its relationship to solar wind. On the upper right, you see a plot with 4 curves. The top curve here is for very high solar wind speed, more than 500 meters per second, and the bottom plot is KP values for very slow solar wind, less than 350 meters per second. And so you can see there is a good correlation between solar wind speed and KP. And from left to right, you see the IMF clock angle. So here in the center, we have northward IMF, and correspondingly we have low geomagnetic disturbance, low KP values. And here on the sides, you see much higher values in KP for southward IMF. KP also has periodicities. Here on the lower left side is shown the periodogram for the almost complete KP series. And you see there's a very strong peak at 27 days, which is due to the solar rotation. And since there can be several sunspot groups on the solar surface, there also come these 13.5 and 9 days maxima in the periodogram. And on the bottom right side, we can see 2 features of KP. The one is the seasonal dependence. So going from left to right, we go through the year, and you can see that the springtime and fall time equinox have mean KP values which are about 1 unit larger than the corresponding KP values during summer and winter solstice. And you can also see the universal time here from 0 to 24 hours. And of course, an index should not have a universal time dependency if it's mostly controlled by things like solar wind properties. But this dependency actually is not very large. It's only a unit of 1/3, which has this, and it shows that the local time corrections done for the individual stations is not perfect in this process of producing KP. There have been other indices like the AM index, and they tried with more geomagnetic observatories a better distribution to produce like a better index, which also has a better universal time independency, but still KP is basically always very useful as an index, and we hardly observe any situation except for UT dependence investigations where KP is not working equally nice as AM, for example. Right. So I would like to say 3 short things, which I don't want to talk too much about it, but why is KP so useful for geospace studies? Well, we have seen it's depending on solar wind. It's also depending on the coupling of the solar wind to the MIT system. That was the seasonal dependency. And we know from the nice paper by Thompson 2004 that KP correlates very well with the equator auroral boundary and during geomagnetic storms. What you see here in blue in the plot is the auroral zone. as kind of the mean auroral oval, but during magnetic storms, the auroral oval increases and the electric currents there get closer to the KP stations, producing higher values. But there's also a change in the secular variation of the geomagnetic field. The geomagnetic field is, for example, pushing the geomagnetic North Pole away from Canada, and that has as a consequence that the auroral zone is also moving. Since 1932, this was by about 5 degrees of geomagnetic latitude. And this effect, if you look at integrate over all stations and the change of the auroral zone, then this will have affected KP since 1932 by a unit, by about 1/3 of a unit. And I also want to mention that the definitive and the near real-time KP values, they differ a bit, because the definite KP values, they are produced by the operator, the K values used for the KP, they are calculated by the institutes operating the observatories, and each has its own favorite algorithm to do so. Whereas when we calculate real-time data, we just get the data and use one algorithm, which typically is regarded as one of the best, here by Saxdorf and others, 1991. And a few years ago, we started to rescale our near real-time product so that the difference to the definitive KP now is very, very small. Right, we also have a new web page for the distribution of KP and also the new indices, HPO indices, or HP30 and HP60. And you can use the barcode to get there. Some of you might remember this traditional, I would say horrible World Data Center format, which was very complicated to read. We have, of course, we still do distribute that, but we have now JSON formats, very easy to use ASCII formats for non-experts, so they can be loaded into spreadsheets very easily. We still have the beautiful musical diagrams for KP. We have web services. We provide you MATLAB and Python code to download it directly from the server. We provide also the derived indices like AP and the old CP and C9 indices. You can also get data files containing sunspot number and solar flux, F10.7. It's actually a very, very nice resource if you want to produce plots of these indices. So you can go there, zoom into the time periods you like to have, and download in various formats. You can register for a newsletter, so we keep you updated on any changes that we have with our operations here. It's a CC BY license, so it's free even for commercial use. But of course, acknowledgement is mandatory here. And it also has a link to our space weather page where you can get the KP and HP60 forecasts with the barcode down here. Right, these are two screenshots from our web page. On the left hand, the data download. On the right side, you see from June 15 and 16 KP values on the bottom. HP60, that's our hourly index in the center, and HP30, the half-hourly index in top. So a direct comparison of the old and the new indices. Right, the new indices. HP30 is a half-hourly index, and it has a linear AP30 index with it. And HP60 as an hourly index and the linear AP60. And you can see in the first plot here, the relationship between the quasi-logarithmic HPs and the linear AP indices here. And since it's an open-ended index, we don't stop at 9. We have values basically open-ended. I'm only plotting here up to 12. And this having more index values in this range allows to give a much more nuanced picture of very strong geomagnetic events. And the frequency distribution of the index is a very important thing. So we designed our new indices in a way that they have the same frequency distribution as KP. And these are plots here showing always 3 years. And they show, let's have a look here at 2001 to 2003, which was a year with a lot of geomagnetic activity. So here you have all 3 indices, KP in green, HP60 in blue, and HP30 in red at the occurrence rate. And during these 3 years, very high magnetic activity, all 3 indices have the same occurrence rate. And now if we go to 2007 to 2009, very quiet geomagnetic conditions, again, the same 3 indices, they have the identical distribution of index values to each other, but very different to the other year with the high magnetic activity. So that's exactly how we would like our new index to behave. But the plots before, they were mostly emphasizing values of low geomagnetic activity, because you can't see the KP9 values in such a plot. So here I show you a comparison of 2 strong geomagnetic storms. The top one is a storm with a very low DST value below -400. And you see in the 3 colors the old and the new indices, they behave very similar. And there's also on the right side here a very good correlation between the old and the new index. Here is the old index, the KP, and the new index is the half-hourly index, for which we took 3 hourly means to compare. And the same here for the Halloween storm in the lower panel, where you can see that our new indices, they got values up to 12 minus, and still a very good correlation to the old KP. Now we have a higher time resolution for this new geomagnetic index than before, and there is a superimposed epoch analysis here shown over almost 2,000 isolated substorms from a list by Newell and Bieler. And at 0 hours here, we have the substorm onset time. In the top panel, you see the auroral electrojet index. So there's a 1 minute time resolution index. In the next panel, you see the same for our new AP30 index. Then comes in the next panel, the AP60 index with 1 hour resolution. And down here comes the AP index with 3 hour resolution. And the AE index peaks after 1 hour and is basically back to background after 3 to 4 hours. KP cannot show this, AP cannot show this, but our new indices nicely show this. That means that we have a physically meaningful information here in the new index, which is not resolved by KP. And this is a bit a difficult plot, but one I like very much, because it shows firstly how our indices, the old one, KP in the bottom, HP60 in the middle, and HP30 in top, are related to other open-ended indices. And here we have on the left side the Newell coupling function, the auroral electrojet index in the middle, and the polar cap index on the right side. And you can see here for the dark black dots, this is the index values up to 9 minus, and how they are related very similar. Like KP relates to Newell in the same way as HP60 and HP30. And the AE index and the polar cap index do the same thing. Each in its different like dependency, but for all indices, for all our indices in the same way. And then we have the green curve. This is a third order polynomial fit to the index values from 0 to 9 minus, and then extrapolated to higher values. And we compare this green line with the measured data points in our new indices, which are the gray dots. And then we produce the yellow dot here, for example, for the HP60 and the Newell coupling function. And we find that the way how we extend HPO beyond 9 makes a lot of sense when we compare it to that best third order polynomial fit to the other values. So I think that's the last slide for today, except the summary and the outlook. So I gave you a description of KP as we do it in the moment, and it's published in a publication by myself from 2 years ago. The original publication and the index come from Bartels. I have shown you our new data portal. That we have looked at the new indices, HP30 and HP60 publication. The reference is here shown again. The HPO indices are KP-like. I hope this was convincing. And they have a higher time resolution, 6 times higher in case of the HP30. they are open-ended. We can already see that they have a lot of good potential for space weather services, for data selection also, we have seen that, and as a model input for geospace models. And in the moment, we are working on a new project because HPO, that's kind of the name for the HP30 and HP60 together, only goes back to 1995, and we want to add another 10, 11 years of HPO data going back to 1984. That will be particularly nice because there have been very strong storms in 1989 and in the early 1990s. And I would not only want to thank you for your attention, but also the institutes that operate the KP observatories and are providing data to us. Thanks a lot.
Thank you, Jürgen. These are really cool. It's nice to see new indices that are faster and have a nicer dynamic range. As you mentioned, I think this will be really important for space weather applications. We had a first question from Jason Durr, but I think it was answered in your last few slides there, and I think he agrees with me. So we'll move on to the next question, which comes from Dave Pitchford. He's asking about the stations that you show in the South Atlantic anomaly, and he's wondering if these might be able to give useful information regarding the dynamics of the inner radiation belt and what is happening there. Do you have any thoughts on that? David also opens it to the rest of the audience as well.
Right, let me move to the slide. So our main motivation actually to set up these stations has been to observe things like SQ, DST in that region, so that there's definitely a DST contribution, like the stations here. They have very nice latitude for DST information, but also for SQ information. We monitor the magnetic field, so we see how the South Atlantic anomaly is changing, and actually we are observing that there's a second minimum now starting to develop around Tristan da Cunha here, TDC station. We see this from satellite, geomagnetic satellite data, but I'm not a big specialist on the radiation belt, so I'll give this back to the audience.
Yeah, with the magnetometers alone, I'm not sure how much we can gather. They're quite low, and we might be able to infer some field line currents and stuff from them, but precipitation and whatnot, I think, might be quite difficult with the ground-based magnetometers in the South Atlantic anomaly. But with it expanding and with stations there, it's definitely something to start looking into in more detail.
Right, and we are planning in the moment, we already got the funding and we are currently preparing to get all-sky imager and VLF receiver and a rheometer to our Antarctic station, which in terms of magnetic field is also strongly affected by the South Atlantic anomaly actually.
Cool, that should give some really neat results. So Willem has a follow-up question regarding the indices. For the indices, the HP30 and the HP60, is their main application for characterizing strong geomagnetic storms, or do you see other applications that these can also be used for?
I think there are many more applications. There are so many applications for KP in the moment that I don't even dare to start naming them. I mean, it's everything. It's ionospheric stuff, plasma stuff, radiation stuff, thermospheric drag, and so on. And I think all these can be addressed with the new indices. And our aim to have a similar KP-like index. Our aim was to do this because then it will be pretty easy to infer results that are well known or relationships that are well known for KP already, also for these new high time resolution indices. But of course, we are very exciting. We are waiting for the big storms and see how our new indices are working then.
Yeah. I mean, from my point of view, I quite like geomagnetic data, especially the ground mags. And I think one of the coolest things here is that you've extended it to 30 minutes. I think that has huge applications for space weather past the 3-hour index. There's a lot of things, well, almost all space weather activity responds much faster than 3 hours. So having something that we can drive a model that is characteristic of space weather timescales, I think is going to be really, really important.
Yes. Also, one thing we can see is that when you start making empirical geospace models that in the previously, say, some parameter measured from a satellite, and previously you make data selection with 3 hours, then the relationships are much more blurry when you compared to when you have a very sharp, very high time resolution index to select things. So I think we will see a lot of improvement on that side too.
Mm-hmm. Yeah, absolutely. Well, thank you again, and thank you, Shannon. I think we had 2 really great talks today. So thank you guys for presenting, and I hope everyone has a wonderful week, and we'll see everyone next week for our next seminar. Bye for now.
Thank you. Bye.